So we are group 6, and I'm going to introduce you to the topic of our project, whose name is FerroSilva. FerroSilva is a project that has its origins in the Royal Institute of Technology of KTH in Stockholm. And the idea is to utilize the chemical properties of biomass to create a fossil-free iron raw material. Steel making is the process of producing steel from iron ore or scrap. Today, there are two major commercial processes for making steel. They are called basic oxygen steel making, which has liquid pig iron from the blast furnace and scrap steel as the main feed materials, and electric arc furnace steel making, which uses scrap steel or direct reduced iron, DRI, as the main feed materials. As you can see from this graph, the production of steel plays an important role in the production of carbon dioxide. The demand for steel is also growing, and the amount of scrap is not enough to satisfy this trend. Moreover, the steelmaking industry plays an important role in the world economy. It involves almost 100 million people, and it's worth 3.8% of the global GDP. In order to drastically reduce the overall CO2 emissions from the production of steel, the development of breakthrough technologies is crucial. Today, a large number of promising projects are ongoing in different parts of the world. One of those is FerroSilva, which scope is to create a sustainable steel production process, preserving the typical advantages of secondary process, also in the production of high-quality steel. By combining the gasification and reduction processes with carbon capture and storage systems, a carbon sink can be realized, and this brings to net negative carbon emissions. So the technology for FerroSilva concept is available today, but the combination is new. This slide gives an overview of the technology's readiness level for each one of the processes employed in the FerroSilva process, which are gasification of biomass, reduction of iron ore to produce DRI using natural gas, and finally the combination of the two, which means reduction of iron ore to produce DRI using gasified biomass with integrated sub-processes. We consider the first one, the gasification of biomass, to be at a level 8 of readiness. This means that the technological systems are complete and proven in smaller industrial scale. So given that the requirement for FerroSilva was around 100 megawatt, we believe that 8 can be assigned with a good level of confidence. The second one, which is a reduction of iron ore to produce DRI using natural gas, is currently at a level 9 of the scale. This because Midrex process is industrially proven, and it has been used for around 50 years using natural gas so far. Finally, the combination of the previous ones, which means reduction of iron ore to produce DRI using gasified biomass with integrated sub-processes, is at a level 5 or readiness. We consider so because we can produce the same composition of reducing gas, syngas, by gasification of biomass, as in the natural gas-based processes. But the combination of the two technologies has not been demonstrated in relevant environments yet. So now I leave Francesca going ahead with the presentation. Please, Francesca.
Thank you, Francesco. Next slide, please. The choice of the gasifier was not easy, as there are many existing technology, and it was necessary to find the one that allow to obtain the syngas with the characteristic required to produce DRI. So, to do this, we build an evaluation matrix giving different weights to each feathers in order to enhance the most important ones. In this way, we obtain a ranking of the technologies that allowed us to identify the two best technology. We then determined which one was the most suitable by comparing them with the design requirements, and the fluidized bed reactor was the winning technology. Similar reasoning was used to decide which gasifying agent to use, and steam plus oxygen was the best choice. Next slide, please. Okay, to make the reduction, we have chosen to use the Midrex process because it has a lot of advantages. It's the most common and consolidated way to produce DRI. And when combined with BECCS, it leads to the best net negative emission balance. And it's a flexible process since it has few requests on the gas quality. On the other hand, it is economically feasible only in countries with low natural gas price, but the use of syngas can solve this problem, making it possible to use Midrex also in Western Europe and other geopolitical areas with good access to biomass. Giovanni, please.
Okay. We did this slide just to give the dimension of the plant we are speaking about. Our case study is about a 500 kiloton per year plant. But just to study the possibility of upscaling, we refer the model on the production of one of the largest steel plants in Europe. The production of 6,000 kiloton per year of iron, as it was in FerroSilva of Taranto, will need a 12-time bigger plant. In both the dimension of the plant, there are no problem related to the availability of biomass. Of course, a plant of 500 kiloton is preferable because it allows a supply of biomass at a short range and therefore lower emission related to the transportation. The typical power of a biomass gasifier is some 10 megawatt, but in literature we found a gasifier up to 700 megawatt. It will be probably necessary to use multiple gasifiers in parallel to produce the amount of syngas required by a larger 6,000 kiloton plant. In both the plant scale, the amount of CO2 treated by CCS are much lower than those processed in existing plants such as Petranova. Next slide. Okay. Here we have a SWOT analysis, which is strength, weakness, opportunities, and threats related to FerroSilva. Among the strengths, we can say that FerroSilva is a climate-friendly process that uses infrastructure already in place and leads to comparable cost to currently existing process. In addition, FerroSilva utilizes biomass that is often considered waste. About the weakness, we need to have a low carbon intensity on the collection and transportation of biomass. Another weakness is linked to the biomass gasification because the current scale is typically some 10 megawatt, but FerroSilva needs about 100 megawatt. Among the opportunities, there is the possibility to spread the process also outside Sweden, the creation of a network between forestry and steel industries that leads to new business opportunities. Then FerroSilva can take advantage of incentives and legislation aimed at reducing emission. The threats about FerroSilva include that it might not be lucrative as using syngas produced from natural gas, biomass versus agriculture, and the unsustainability of the process in dry areas due to the shortage of biomass. Next slide. Okay. To estimate the potential of the FerroSilva process, we made a model. We found out that the implementation of FerroSilva to a standard Midrex plant leads to an additional investment cost of about 150 million. But considering the saving related to the price of the raw material and the cancellation of the carbon tax, the payback period is about 2 years. Regarding the emission, from the graph on the right, we can see that FerroSilva can lead to a net negative CO2 balance. Okay, next slide.
Okay, about the risk of this project, we divided them in 3 colors according to risk level. Green is low risk and red is high risk. In the lowest level, there is the possibility of having biomass shortage in the first period, but this problem has already been solved by including biomass supplier in the consortium. The risks marked in yellow are 2. The first one concerned the need to find efficient storage places for the removed CO2, but it's not a too serious problem, because when injecting CO2 into the storage place, if it has some leaks, it's immediately noticeable. The other yellow level risk concerned the difficulty of finding financiers to build the first plant, but perhaps increasing research can be a good way to increase investors' confidence and curiosity on this project. Among the most important risks, there is the possibility of not finding the right gasification process that leads to obtain the syngas with the desired characteristics, and maybe it will be necessary to foresee an intermediate stage between the gasifier and the shaft furnace to condition the syngas. Another problem is related to possible methane emissions throughout the whole process, and this would put the negative emission balance at risk. To solve the problem, maybe a better monitoring of emission along the plant will be needed. Next slide, please. In order to successfully develop a FerroSilva project led by the project management, the consortium should include a research institute to ultimate the study about this new process, like KTH, Chalmers Technical University, and IVL, equipment supplier to build the plant, like Svesgog, Farmers Cooperative, Danieli and Midrex, biomass and iron ore supplier to feed the plant. About the biomass, we have Svesgog and the Farmers Cooperative, and for iron ore, the mining companies from Sweden and Norway. And then steel industry and steel users like automotive industry should be included in the consortium too, because they are the final users of FerroSilva products. And they are interested in this project because it allows to obtain clean iron source, low impurity rate in steel products, and negative CO2 emission. Next, please. At the end, why EIT raw materials should fund this project? Just because innovation in steel industry has a huge impact on society, economy, and environment. The utilization of CCS technology follows the guidelines in IPCC for the decarbonization of the big industries. This process led to a net negative balance of CO2, and it's a combination of technology that are already proven on their own, so there is a low risk bound to innovation. For this reason, the project has all the credential to be an excellent investment. Next. Here are some sources we used, and at the end, thanks for your attention.